I want to tell you a little bit about my process, what I do, why I wake up every day, why I'm so happy to wake up every day. And because I'm an engineer, I like to bring everything down to either an equation or a figure. And in that case, it's going to be a figure. And it's the figure from Joseph Tainter, who wrote a book called The Collapse of Complex Societies in the 1980s. I think it's 1988. And what you see here is on the x-axis, we have level of complexity, and the y-axis, we have benefits from complexity. That has nothing to do with complex systems or complexity theory of complexities. Complexity is really stuff. So you have a system and you're adding stuff to that system. And so you're adding complexity as in, just stuff to that system, and you're getting some benefits from it. So the example that I would use is, let's say you're the first settlers in London. You're there, you need to get some water from somewhere. You're probably gonna build, a lot of infrastructure and get some water from the Thames. And so you're gonna add a lot of complexity to your system. You're gonna get a lot of benefits from it. And then London is gonna grow again and again and again and again. And at some point, you just might not be able to rely on the Thames as much anymore. So you'll have to maybe go to the ground. And what you'll do is you go for the second best option. So you might go for groundwater, and then you're going to have to, again, build pumps and build a water distribution system and treatment plant. And you're going to add a lot of complexity to your system. But because it's the second best option, the benefits are just not as large. And the way I see it is, so the theory goes that if we go on like this, what we get each time we add new things to the system, we get diminishing marginal return. So each time we're adding the new something, that new thing is giving us fewer and fewer benefits as we go along. And so what happens is, if you don't change the way that you're doing things, either you collapse, so that's a scenario A, and that's happened to the Roman Empire, that's happened to the Maya civilization, or you do something different, and what you're able to do is to go up and just do things differently and to keep going without collapse. And that's the scenario B. And at some point, the scenario B should brings you to a point where, again, you might collapse or not. So scenario A, the Roman Empire, that's one example. Scenario B, an example was the Industrial Revolution, which really allowed us to have bigger and bigger cities. But now we have the problems that we know, right? Problems with sustainability, with global warming, climate change, et cetera, et cetera. So it's really time to rethink the way we do things. And in engineering, a lot of what we do right now in the practice are inherited from the 1950s and 60s, and are really the knowledge that got us into the problem where we are now. So the way I try to think about cities and infrastructure systems from an engineering perspective is really to try to come up with some new thinking, just novel way of looking at it. I'm going to give you two quotes now. These are my two favorite quotes in the entire world. The first one is from Einstein, and it's, "We cannot solve our problems with the same thinking we used when we created them." So that's really why, I love network science. I love science of cities. Now I love machine learning, really just because it's different thinking, a different way of thinking about problems that we have, different way of thinking about cities, different way of seeing cities. And because we can't just use on the same, again, knowledge that we developed that got us into that problem in the first place. And that's why I love all those new techniques. And the second one is from an artist, and the artist is Frank Stella. I always ask people, and do you know who Frank Stella is? In engineering, no one knows. Sometimes in urban planning and urban geography, This is an American artist who was first a minimalist, and then his canvases were pretty amazing, and he really emerged from the canvas. So instead of having a canvas, it really started to become a 3D thing, which I really like the process. And he has a quote, which is, "Boundaries are defining but not limiting." And I like that a lot, because usually, at least in engineering, a transport person is only going to do transport. A water person is only going to do water. And then if you say, well, but the transport and water realm, they interact, they're not going to think about it. They're going to say, well, this is the transport problem. I only think about my water problem I have. And I like to say, boundaries are defining but not limiting. It's not because water is water, transport is transport, okay. There are boundaries that define the systems, but that's not why we have to limit ourselves to only looking at those systems individually. And that's really what I'm trying to do. If I show you this picture, I'm going to ask you what you see. John might tells me, "Oh, what an eyesore. It's the shard. I hate it." But hopefully a lot of you are going to tell me what you see is the city. It's London. It's everything. I'm hoping that not one of you are going to tell me, well, what I see is a bridge and I see just structural engineering elements, or that you're going to say, oh, I see a road, so I only see transport, or I see the Thames, I only see a water, an open channel, for example. It's everything together. And somehow, so what we've done as cities became more and more complicated in the 1800s and 1900s, we've had to divide the way we look at cities and really to specialize into transport, water, et cetera, et cetera. But I think for at least for some of us, it's time to look at everything together. And that's what really urban engineering is. The way I try to explain it, when I tell people what I do, they say, well, so you're an urban planner, you want to plan cities. I say, well, not really. Urban planning is more about, they look at people and where you put schools and when you put, urban planning. And what I do is really looking at engineering systems. So that's why I say it's urban engineering. Urban engineering is really urban planning, but applied to engineering systems within cities. And for that to happen, you just need to have a lot of knowledge. And for the past 15 years, really, I've been learning a lot. I've been learning a lot about urban planning. I've been learning a lot about electricity generation and distribution, about water treatment, stormwater management. I might talk a little bit about stormwater management, but to me, it's the leading sector that's transforming cities in the entire world right now. And I love it because it's really just stormwater management, which is not the thing that you think is important, but it's really completely changing cities. There's, of course, transport. I know, I'm sure a lot of you have done a lot of transport. We can see the four-step model here. We can see the microscopic, the fundamental flow diagram. Learned a lot about buildings. I had to go back to 4 years, lots of heat transfer that I had completely forgotten, and green roofs and a lot of things, a lot about solid waste. Solid waste is one of the newest ones that I've learned. I really didn't think it was going to be interesting, and I'm now absolutely fascinated by solid waste. It's a wonderful, wonderful discipline. And just recently now I'm getting more and more into telecommunication, both the analog telecommunication, the phone, the television, as well as the internet. One of the ways that we can get everything together, there's that concept of urban metabolism. I don't know if you're familiar with it, but it's really about looking at cities and looking at everything that's coming in, what is being produced inside, and everything that's coming out. And when I say everything, it's really everything from construction materials to food, to the energy, to water, just about everything. So there's urban metabolism, infrastructure integration. There's that new lens that I'm trying to bring, science of cities, machine learning. And of course, so what I did is I created a class to learn all these things. So the best way to learn something is to teach it. So I created the class to force me to learn all these things, which I did. And when I learned all these things, I wrote them together for students to know them. And of course, that led to a book. So that's my sort of my little claim now is I do have a book about urban engineering for sustainability, and actually need to thank Mike Batty for that because he introduced me to an editor at MIT Press. So that's where it's published. So don't buy it. My goal is not to make any money out of it. If your library gets one, great. If you do want to have a copy of it, I do have the original draft. So it's not edited, it's not formatted, but I'm more than happy to share it with you for free. And really, again, it's about defining what sustainability is. There's something like publishing forecasting, urban planning, electricity, water, transport, building, solid waste, urban metabolism, science of cities, machine learning, just kind of get everything together. And for me, that's really, again, a new way to look at cities. Or maybe it's an old way that we're just revisiting now because we over-specialized over the past. And so that's really urban engineering. And then once you start to look at everything together, you start to think about infrastructure interdependencies. Here, this is just some infrastructure that we have on the UIC campus, University of Illinois at Chicago campus. We have the distribution lines here for electricity. That's the electrical lines, the sewer system, water distribution systems, all the buildings, all the transport here, all the roads, the natural gas system, and the hot and chilled water. And what I like to say is that all those infrastructure systems, they all live in the same space. So somehow, a transport person is only going to look at transport. But again, all of them live in the same space, and they're all interrelated or interdependent in some aspects. I'm not going to go over this table, but that just tells us how transport, it depends on water, utility, electricity, telecom, how they're all interdependent. And right now, the way that cities have evolved, I think in the past, for forever, but at least in the past 100 years, is that we have those interdependencies, and they're not designed for. They're there because we just build, but they're ad hoc. They're not controlled for. So right now, I see those interdependencies as limiting factors to what we can do. And one of the things that I'd love to be able to do in the future is to control those interdependencies. And I think that's really, really important. And here's another quote for you that I absolutely love, and I tell all my engineering friends. It's from Don Norman, who wrote an amazing book called The Design of Everyday Life or Everyday Things. I forget the quote, but here it is. It's engineers and business people are trained to solve problems. Designers are trained to discover problems. A brilliant solution to the wrong problem can be worse than no solution at all. Solve the correct problem. And I love this because I do think that engineers tend to solve the wrong problem again and again and again. a water treatment person is going to see that all the problems in the world are related to water treatment, and we should treat water, and they're going to build water treatment plants, for example. A transport person is going to see the road just as a medium to carry cars or buses. They're going to forget the roads are there and that they're there for stormwater management. They might forget the roads are there, and they also have gas infrastructure below them and electricity infrastructure below them. And so the value of a road is not just to carry cars; it's also for all those infrastructure systems. So discovering what the real problem is very difficult, and it's not something that we're taught in engineering. Usually, what happens is that a municipality or a company comes up to us with specifications and say, well, this is our problem. We need to solve it. We want a solution. And so the engineering is going to come and say, all right, this is your problem. This is the solution. I'm going to implement it. Not even going to question whether the problem is really the problem in the first place or not. So how do we identify the problem? And that's really something that I've been asking myself for the past couple of years, and I'm really gearing up to it. If I show you this picture from an urban design perspective, what's happening here, and if I show you this picture, what's happening here, if I ask you which one is better, do you think? Which one is good urban design? Which one is bad urban design? I think over the past, I don't know how long, several decades at least, we've been able to say, well, this is better. This is preferable to this. We have good urban design. It tends to be more sustainable, more lively, more healthy, more walking friendly. People are there. Bad urban design is unsustainable. It tends to be low density, car oriented, no access to shops. So accessibility is a big one. So I do think that we have sort of good and bad lessons for urban design, urban planning. And for urban engineering, it's a much more difficult. Again, I might tell you some desirable traits of a water system, but how does it fit within the overall context of the city? That's much more difficult. We do have some objectives, sustainable, resilient, adaptable, distributed. That's good. What is bad is unsustainable, vulnerable, rigid, centralized. We don't like that. But I mean, what do they mean when you operationalize these adjectives in a city for urban engineering? What does it mean? And that's very, very difficult. I mean, I'm really wrestling with that. One of the things we're doing now is and we'll talk about smart infrastructure a little bit after, but we're smartifying everything. So we're putting sensors everywhere, and we're assuming that the city is going to be better. But is it really going to be better, or are we just creating a new dependency? And now if that telecom fails, we're actually worse off than we were in the first place. It's really not obvious. One of the things that I've done a few years ago was to think about this integration-decentralization matrix. I knew that integration and decentralization were generally traits that we were looking for in infrastructure systems. And so I just have this simple matrix, and I have integrated on one axis, and then integrated or separated for any infrastructure system, centralized or decentralized. And where are we now? And I thought that right now we're right here. So we tend to be overly centralized and separated. And the picture I have here, that's the Chicago TARP system. So in Chicago, the way that we deal with stormwater, so it rains a lot. When it rains a lot, the water has to go somewhere. And it falls on the buildings and falls in the streets. And what's happened is that over the past 100 years or more, in places like London, way longer, we've really been paving streets. So all the surfaces, all the grass and the trees and the native plants, and all that was there before that could soak in some of that water, all those impermeable surfaces were turned into permeable surfaces, right? That's concrete, that's asphalt. And so all the water that falls into the cities now has to go somewhere. And because the surfaces are impermeable, it's just going to go to the path of least resistance. It's just going to follow gravity. And the way it happens now is we've built in such a way that it falls on the houses, and it goes to the streets, then it goes to the curb, then it goes to the sewer system. And of course, the sewer system was designed 50, 100 years ago. And so it's way too small. And so the sewer systems that we have now are backing up all the time. And I'm sure you have flooding problems in London as well, and especially in older cities like London and Chicago that have a combined sewer system. And so the way that Chicago thought about dealing with the problem, the way that their strategy to solve the problem in the 1960s and 70s was to build massive underground tunnels below rivers where they could store all that storm water when the system was over capacity, and when the rain was stopping, they would pump everything back up. And that's really, for me, that's a perfect example of solving the wrong problem. The problem is water is falling. It's always going to fall. It rains. Before the surfaces were permeable, so water could infiltrate in the ground. It's not anymore. So is the solution to over-engineer things and build those massive underground sewer systems, really, bigger than subway systems, or as a solution to make this services a bit more permeable. And so that is a typical solution from the 1970s, which is, again, over-engineering, all concrete. And the funny thing is that they're all below the waterways. Part of it is because the City of Chicago Water Management Department, they own the waterways. I was thinking, why not below highways, for example? It's like, well, the highways belong to the Department of Transportation. And so if we want to do that, we have to work with them. We don't want to work with them. We only want to deal with whatever we're responsible for. So that's where we're going to go with the waterways. So that's really the current paradigm, overly centralized, overly separated. What we're going more and more now is toward, it's a bit of decentralization, but it tends to still be very, very separated. And the good example is our solar panels, or solar energy in general. So now we can distribute it on roofs, just about everywhere. But it's distributed, it's decentralized, but it's still very much separated. My question is, whenever I ask, especially students, what do you think we should do to make cities more sustainable? The first thing they mention, really the first thing, is solar panels. And I always wonder, why solar panels? I mean, you can use roofs for many different reasons, many different things. You can have green roofs, you can have gray roofs, you can use them for many different reasons. So why solar panels? And it's still, again, very, very distributed, but that's, one avenue that we're taking. Another one is to do still very centralized, but more integrated. And in my experience, that's more rare. There tends to be few examples here and there. That's an example here in Kuala Lumpur that I like. It's essentially a tunnel for traffic. Kuala Lumpur had massive traffic congestion problems, and so they built a tunnel. But what they decided to do is instead of making just a tunnel for traffic, they also made it a tunnel for water. So whenever it rains too much now, what they do is they actually shut off the tunnel and they flood the tunnel with water, with storm water. So it's a hybrid between the tunnel and that those underground tunnels that I mentioned in Chicago. So in Chicago, it's different because the system is combined, so you can't have it because it's you do have the human sewers, sanitary sewers with the stormwater mixed. Here in Kuala Lumpur, they're only, to my understanding, they're only using the separate. It's only the stormwater. But that's an example of localized integration. So again, you're starting to integrate different infrastructure systems together, but it's still very centralized. And what we might want to aim for in the end is really to have integrated decentralization. And that's where, again, you're integrating different infrastructure systems together, and it's over entire cities. And the best example for me is again, stormwater management. And it's really, again, making those surfaces more permeable with, for example, green infrastructure and low impact development. This is an example here in Copenhagen, where they've completely changed the area from having, again, just a road with a gutter and everything was going in the sewers. And even here you have some grass, but grass actually doesn't soak up too much water, to having a lot more native plants and even have conduits, so that the way that you're channeling the water actually goes to where you want it to go in a much more effective way. So just different way of thinking. So that's really, urban engineering and urban engineering the future. Trying to think, more creatively about the future is very, very difficult. That's actually partly why we've got that book, the one that John mentioned, the one, we have one of the contributions comes from Mike, which is Urban Infrastructure Reflections for 2100. Really try to think, long-term, because 2100, there's no way our models are that good. So you just have to be creative. You just have to think about science fiction. And when you do science fiction, you try to think more. You try to, I wrote a short story. I was trying to imagine a person during the day, what they were going to do, how their lives would be impacted, by things that were around, what would be different from a culture perspective. I also really like I like the process of thinking of humans. So I was not thinking about just technology and how technology is going to be, because technology is just a support for humans, right? So it was more humans, where we are, what do we need to be happier? What do we need to have a lively city? And then to maybe imagine some technologies to be in support of it. So that's really urban engineering. I wanted to pause here. That's my little experiment. So we're going to do this a couple of times. So I wanted to pause, questions, thoughts. What do you think the future of infrastructure is? What do you think about, just infrastructure in general and where we're going? So go for it. I realize that might not be too many questions. It's usually the case. That's why I thought I'd do an experiment. If you have any thoughts, we can talk about it in the end as well, later on.
Well, All right, I'll bite with a question. What do you see as the kind of, if you will, right? So localized integration also implies a kind of technical diversity, which increases complexity and consequently the kind of challenges of upgrading infrastructure over time. Because, one of the things we have here in London is lots of historical infrastructure that's very hard to upgrade. So for instance, we have our deep tunnel tube, which, we can't do what New York does, which is cut and cover. And, we fix one line while we upgrade a different one. Similarly, our telecoms infrastructure, I live in an area where there's no fiber and they have no plans to fix it. So how do we navigate kind of the upgradability of localized integrated infrastructure?
I mean, that's a great question. That's absolutely a great question. I don't think there's a blanket solution for everything. But at the same time, I don't think that just doing what we've been doing in the past helps. I'll give you an example, because I think actually telecom is a field that I think in urban engineering we have much to learn about. I learned recently that in telecom, so before in telecom, even phones and water and everything, the emphasis was on the quality of the service. So you want to make sure that if your call, it doesn't drop. If you have a transit system, you want to make sure that the bus is on time. If you have electrical, grid, you want to make sure that you always have power and there's no problem. So the quality of service was really the main focus. In the telecom industry, what they did is to change, instead of doing the quality of the service as the main focus, they changed it to the quality of the experience. Mm-hmm. So you might, your internet might not be, it's a bit slow now. I don't know why. And somehow you don't care too much because the experience is good. Sometimes it's a bit slower. Sometimes it's a bit higher. It's not so much on the quality of the service. It's the quality of the experience. Even in transit, I find it now with apps. Before, I would have to wait 10 minutes, 15 minutes outside waiting for a bus. I would be really annoyed. Now I just take my app. I know it's coming in 2 or 3 minutes. I don't care if it's late because I don't have to wait that much. So the quality of the experience really all of a sudden makes everything different, right? What you think about is just not optimizing so that your service is as good as possible. It's not to be 99.999% on time. It's to make sure that the people who in the end are the people, the people are the people using the service, that they're happy. And if they're happy, even if the service is not optimal, that's fine because that's all you want. So that's just for me, it's a completely new way of looking at it. Even if we think about it in terms of water, so right now we just expect that when we open the tap, water flows out, and it's drinkable, right? We just expect that, and I do think that the way that we distribute water right now makes no sense. When you think about it, what we have are massive water treatment plants that treat a lot of water, and then we push everything in water pipes, and we have millions, at least per cities, thousands of kilometers of pipes that are always under pressure. Because if it's not under pressure, you might have groundwater seeping in the system. And that happens, it could be contaminated. And if it's contaminated, then you need to issue a boiling order. So instead, what we have is those pipes always pressurized. A lot of them are breaking because they're old and we need to change them very, very rapidly. So it's just not resilient, right? It's very vulnerable. And really in the future, we should think about a different way of doing things. I don't know what the different strategy is. Maybe it's to have more common secondary treatment process at your house. So what you do is, we distribute water at a lower pressure. The quality is lower, but in your house, all of a sudden now you do have a treatment system there. And so you only treat water maybe to the faucet they actually use, and so that you don't have to over-treat the water that goes in your toilet. I mean, just thinking differently about what we actually want to do with that infrastructure. What is the service that we want to provide, and the experience that we want to provide. And just that, I think, can make us much more creative in the way that we think about infrastructure.
Thank you.
We do have one question in the chat. So by Supriya, and it's my microphone refused to work. I like the terminology integrated centralization. Decentralization, especially for climate measures for infrastructure, is considered a bane. That's a nice word that I don't know what it means. Since there are multiple boundaries within a city and power dynamics keep changing, how do you think this would work from a planner designer's perspective who still work within boundaries of region municipalities? What forms of cross-scalar innovations do we need in planning domain? Bane like a curse. Okay, thank you. There's a quote that I like, and I mentioned it in something recently. I forget what, but I love that Spider-Man quote, which is, with great power comes great responsibility. I like to turn it around. With great responsibility comes great power. A lot of times what we have are those regional entities. In the US, we have Metropolitan Planning Organization, or in Chicago, we even have the Regional Transit Authority, which is supposed to overlook all of the transit going on in Chicago. So in London, you have TfL. TfL has a lot of power, and so your transit system is actually pretty good. I'm sure you're all complaining about the TfL, but I'm sure it's pretty good. Here, it's not as good because that regional authority actually doesn't have too much power. So maybe one of the things we want to do is, again, if we assign great responsibility to an authority, we have to give them great power as well. I don't know if that answers the question, but that's one of the things that I was wondering about, and I like it. I'm not a big Spider-Man fan necessarily, but I like the reference. Any other questions? All right, so I can move on a little bit. If you want, we can talk about machine learning. So let me share my desktop again. Here it is. So these are really questions that I ask myself all the time. The future of infrastructure. What is the future of infrastructure? How do we make it better? What does better mean, right? I mean, again, good and bad, I think in terms of urban design, maybe urban planning, we sort of know. In urban engineering, we don't, because something we do could actually make things worse. The question is, what about smart infrastructure? Is that the solution? So the question is, what is smart infrastructure? A lot of it has to do with ICT, information communication technologies. So SCADA system, I don't know if you're familiar with them. I always forget what it means. Supervisory, control, acquisition, data, something. So these are for electrical systems and water distribution systems and gas distribution systems, sensors to monitor in real time, the flow and the quantity and the energy, for example, in your system. So that is smart infrastructure, adaptive traffic control. That's one. Real-time stormwater control, the smart grid. Is it a solution or not? The thing is, I don't know. A lot of the times, the way that we're sold on those technologies is to improve efficiency. And I don't think that efficiency is necessarily what we want to go for, at least not all the time. Efficiency is a way for me to remember at the beginning the diminishing marginal returns. Efficiency is to say, well, we have all the capacity and we just want to use more and more about it. So we're just becoming more efficient, but we're still within the same realm. So I like to use the word effectiveness more. The thing is, yeah, so what does the use of ICT automatically make infrastructure, does it, and why would it? And is smart infrastructure necessarily better? And that I actually don't know. I am worried about adding dependencies. And I do think that the Silicon Valley, really what they're trying to do is to capture new customers, like capture municipalities, and then they're locked in because they're dependent. And then they just have to cash in every once in a while. Sorry, I did see that there was something in the chat. I'm going to remove this for you, and I'll just have a look at it. There was a very good book in the mid-1960s edited by Loudon Wingo Jr., where there was an article by Catherine Bauer Wester on centralization versus decentralization and concentration versus deconcentration. Mel Weber, an article in it published by Resources for the Future, Johns Hopkins University Press. Oh, the book was called Citizen Space. Thank you very much, Mike. I'll check that book. Thank you very much. So what I'll do now is move to machine learning a little bit. I don't know how much you know about machine learning. I'll assume that you know very, very little about it. And the first thing I'll do is to tell you about it and tell you what we expect. So here's what we like. We get some data for something, we plot it. This is very simple with two variables. What we do is we look, there's an outlier. Oh, let's remove the outlier. When that's done, we can fit a line, we have our model, and we're happy and good job. And then someone's going to tell you, well, let's do machine learning. We're going to put more data. We're going to put sensors. We're going to give you a lot more data, and you're going to be able to do much more of that. Well, look at me. What you get, when that happens, and then you get all your data, and then you plot it, and what you get is this. And this makes no sense. Before you had your really nice fit there, your nice model you could fit, and all of a sudden you have this. That makes your, again, no sense, and you're not necessarily happy about it. And oh, look, maybe there's an outlier. But really, what we actually have, now is with all that data, is maybe just different classes of data, right? We have different behaviors, just different things that are happening. Here, for example, we have class A, B, C, D, and who knows, maybe that outlier is not an outlier, but it's actually a different class. And so machine learning really allows us to do that, right? Machine learning is not to do the same thing better. It's really to think in a completely different way about data. That's why I like machine learning so much. I've been in it now for maybe 6 years, so I'm getting a little bit not as inspired by it anymore. But it really, it changed a lot of it changed the way I was thinking quite a bit. And the first thing about machine learning, which I like, and which is something, I don't know about your field, but in engineering, we tend to be just taught equations and we just apply equations. We like to have closed form solutions for everything. And machine learning is all about algorithms and algorithmic approach. So what we do is we find some kind of a solution, and then we iterate again and again and again and again and again to find how it works. One of the ways that it works is, well, I don't know if you know about k-means clustering, but it's a very simple algorithm that I like a lot, just because it's incredibly simple, but that algorithmic approach is just very powerful and drives us to a solution. The other thing about machine learning is that the algorithm learns by itself, which is pretty nice. It's pretty nice because it can really learn some very, very complicated stuff by itself, stuff that we actually don't understand. And that's the drawback, is that very often, we don't really know what comes out of it. I don't know if you've seen the documentary, The Social Dilemma. It's on Netflix. I watched it. It kind of freaked me out when I watched it. I deleted all my apps from my phone after the Facebook and LinkedIn and Twitter and everything. I deleted everything from my app. And what they do is they do have machine learning to, when you scroll up, what you see below, in your feed, it's not what really is there temporarily, right? It's they actually show you what they think you want to see, and then they put some ads to it. And it's not they as in actual people who do it. It's an algorithm that we don't really know how it works, but it does it, and it just shows you, things bit by bit. And that's the way that's machine learning. It's incredibly powerful. You get goodness of fit that are incredibly high, but a lot of the times you don't really understand how it works. I'm saying a lot of the times, not always, because we are better and better and better at interpreting the results. We have more and more and more measures now out of it that help us at least know whether the model is going in the right direction or the wrong direction. But there are many parameters to tune, and the way that we usually do it is we divide the data set, for example, 80% for training and 20% for testing. Here's a very diagram, not going to go over it, but just about machine learning in general. One of the things I like about machine learning is all those terms. I was really freaked out at the beginning. Unsupervised learning, supervised learning, k-nearest neighbor, random forest, neural network, support vector machine. They all sound, very, very scary. And I think that's one of the actually benefits of those computer scientists. They're just really good at branding themselves. But one of the ones that I like is unsupervised learning here. I really didn't know what that was before. Supervised learning is really your normal regression, your X and Y, you just fit a line to it. That's a regression. That's supervised learning. It's supervised because we do have a dependent variable and we're trying to predict it. Unsupervised learning was you just give data to a model, and it just tries to find some patterns in it by itself. And usually you're going to try to cluster. So for example, I'm going to give different cities into a machine learning algorithm. I'm going to try to cluster cities, see if some cities are more similar than others, and how many groups of cities do I have that come out of it. And then the type of unsupervised learning is for topic modeling. So for example, I can give a lot of abstracts to a machine learning algorithm, and it's going to look for topics that just emerge naturally. And that speaks to me as a complexity scientist, just because I want to know, again, naturally what emerges. And that's what unsupervised learning can do. So it's pretty powerful. So we've used just about everything in my group. We used it in travel choice modeling a few years ago. Actually, one of the big ones, still now maybe, is neural networks. So we tried a bunch of different neural networks. The MLP with backpropagation, that's a very typical one. We used other kinds of neural network, and we applied them for travel mode choice. All right, so to tell whether people are going to drive, take transit, or they're going to walk, or whether they're going to bike. What we actually found that the accuracies were good, pretty good, that they were better than some of the traditional tools that we had. So I was really, really, really impressed, again, because those models tend to be, they're very easy to run. If you want to learn how to do machine learning, again, I think the biggest barrier is just going over the branding, just because it sounds very complicated, but it's not. And running them is very, very easy. The interpretation is something that takes a bit more experience, but it's still there. And the accuracy, again, is very, very good. So we were really impressed, really happy with it. Thanks to that algorithmic approach, machine learning tends to be able to capture highly nonlinear patterns. So there's some really crazy stuff going in your system. You don't really know from a human perspective. We don't really know. Well, the machine learning can pick it up and really, again, just capture those nonlinear patterns. The one thing that I also got out of that paper is that we did come up with 5 different models And then one of the things you like to do with when you do a model usually is, at least in econometric modeling, is you want to have derived elasticities. So if I do this policy, what's going to be the impact of this policy? And what we did here is we have 5 different models. The 5 different models are statistically significant. So we could have essentially written a paper for each of those and said, this is the model that we should take, and now we can do some elasticity. And what we did is we did do some sensitivity analysis by playing with variables. I'm not going to go over that slide, but what I want you to look at is that you see that there's a range of patterns. And really, those different models are going to give you different elasticities or different predictions on the effectiveness or of a policy. And they're all statistically significant. So all of a sudden, I became very skeptical about models in general. How do you trust? Because normally we'd say statistically significant or not. More and more now we realize that it either maybe makes sense or it doesn't make sense. But I'm just skeptical in general, especially if someone tells me, well, if we adopt this, there's going to be an increase in 20% of this. I don't know whether it's true. I don't know whether we can even come up with the confidence interval, but at 20% is, again, I'm just very skeptical in general. But we realized that approach of machine learning, we applied it to water consumption, because I do try to look at, again, a lot of infrastructure systems. We had some really good data for water consumption in the United States. This time we applied it to a lot of models. We had 12 of them, 8 for traditional one, even linear regression, that's right here, and then some more advanced machine learning techniques. We found that one of them in particular, gradient boosting machine, worked pretty well. So here, this is just 1 R-squared. That's just a general goodness of fit measure. We went from 0.3 to 0.6. We really, really liked it. Really, those papers, initial papers that we did, were mostly about comparing different techniques. One of the reasons why we did that was to learn about the techniques, because they all have biases. They all have biases. They all have their quirks. And so we want to learn about them. This is of actual versus normal predicted data. And so we were just trying to learn, and what they were doing, and we could find some differences between random forest and gradient boosting and k-nearest neighbor, and it was very, very interesting. And increasingly now, what we're trying to do, instead of just comparing machine learning models, we just pick one that we think is suited. And what we're trying to do is to move away from just having a good prediction. It's not so much about making sure that the accuracy is as high as possible. It's trying to make sure that the model tells us something about the system that we're dealing with. So normally when you come up with a model, your model has maybe two purposes. One of them is inference. The other one is forecasting or prediction. Prediction is trying to see what's going to happen in the next few years, 1, 2, 3, 5, 10 years. But a lot of times what we want to do is to do inference. And inference is to learn about the system that we have in general. So again, that interpretability, what did the machine learning algorithm learn? We're trying to learn that. So instead of doing just go straight with for the accuracy, we go with, all right, we pick one that we think is meaningful, and then we're going to try to interpret what was learned. And it's funny because reviewers I haven't caught to that. Reviewers still want to ask us, well, why did you select that particular machine learning algorithm as opposed to the other one? Wouldn't the other one give you better accuracy? And we tell them, well, it's not really accuracy that we're looking for. It's really just because this technique has those measures that we can actually interpret afterward. And that tells us a lot about our system, and that's what we want to do. Now, so with that in mind, we also we did some investigation of interrelationships in electricity, gas, and water consumption. So what we did is we just had 3 models, one for gas, one for electricity, and one for water. And we had a bunch of variables, including the 2 others. So for example, in electricity, we have a bunch of variables, including water consumption and gas consumption. In water consumption, we had a bunch of variables, including electricity and gas. And from that, we can actually look at some interrelationships in my hierarchy of how important the variable is in my models. Where are those 2 others? And for example, here for the electricity, that's using something called SHA, but for electricity consumption, we see that the most important variable was whether the building was a residential building or not. But the second one are water and gas. So there are some interrelationships. Sometimes where there might be proxies for occupancy, but they do capture other things. And we try to pick them up. And it's funny because we had I want to say a fairly small data set. It was for New York City. I mean, we did have a few thousand data points, but it's not, millions and millions of rows. But we got a lot out of it. And interpreting what was coming out was actually very, very difficult. But again, those interrelationships is something that we're trying to look into, and that's something that machine learning can do, and it can do it very well. The last thing I want to tell you about in machine learning, which is something where we're really going now, is there's something called causal discovery and inference. So usually when we develop a model, we have a dependent variable, let's say it's water consumption, and then we have a bunch of independent variables, for example, number of people in the household, where they live, maybe level of education, maybe income. And we're going to assume that all of those are independent. And usually that's what we do. And we're trying to predict the dependent variable, but usually they're not independent. So there's something called probabilistic graph models. And these are really graphs, networks like we all know. And what you do is you sort of have the hierarchy of variables, and they get combined together to try to, at the end, predict whatever you're trying to predict. And so normally that's something that you would do just based on domain knowledge, so based on what you know. But there's something called causal discovery, which is still very, very new. There's a lot of work that needs to be done. Right now, the graphs that are done automatically really don't make sense. But I really see a lot of potential in causal discovery, because we could see maybe a hierarchy of variables, and those hierarchy of variables can tell us something about the behavior of people and how they interact with the system, and how, what they want from an infrastructure system. What sort of service do they expect? One of the ways that I explain it is, maybe what we get here is a hierarchy that tells us, oh, those types of households are more environmentally friendly. These ones are not as receptive to policies that are about the environment, et cetera, et cetera. So I do see a lot of potential in causal discovery and inference. Inference is something that we already know, which is, kind of making sense of what's going on in our system. But causal discovery is something that we're getting into, which I think is pretty cool. So now it's time for another little pause. What I have left after is really just 5 minutes, because I know it's 47 now. So I don't know if you want to talk about machine learning, smart infrastructure, if you have anything in mind. Really, the rest is only 5 minutes. So, we do have a couple of minutes to talk about machine learning and smart infrastructure and anything else that you have in mind. Any questions? I'm going to stop sharing right now. Any questions? Any thoughts? I'm hoping that this is relevant to the discussion. I'm hoping. If not, that's fine. I can just.
Background.
Sorry?
I said that'll be my daughter in the background, not knowing how much the microphone's picking up. Well, why don't we finish off and then just move straight to questions and the social bit. So.
All right, perfect. So I'll do that right now. Let me go back here. And so again, based on my experience, so I did write some papers and I was trying to come up with some lessons. How can I participate in discussion to plan future infrastructure systems? And I did come up with a 4-step design process that I thought I would show you today. And I'd love to hear what you think. It is in the book, so if it's rubbish, I hope it's not, because it's in the book, it's self-published. But the first one, I think, is the first thing that we should do is, usually engineers, I think, have an addiction to building new things. And so before we do that, we should really try to control the demand, understand the demand and control the demand, to try to reduce the need for a new infrastructure in the first place. That's something that I think transport people are better at than others. So better than water people, just because travel demand management is a big thing in the transport community. For water, maybe in places like Israel and Singapore, where they don't have too much water, they're good at they're good at trying to come up with policies to reduce the demand. But that's the first thing we should do. So if we have a problem with infrastructure, first thing, let's not build it. Let's try to reduce the demand so that we don't need to build it in the first place. The second one is, if we do need to build it, can we integrate it within the current infrastructure? The example that I have here is for, even if we do need to build some deep water tunnels, for example, for Chicago, do we really need to go under the rivers, or can we just use some existing infrastructure and we just mix it, right? We just assemble it with current infrastructure. Other examples, actually, again, from the telecom industry is, if I ask you the fiber optic cables that are across cities, so not necessarily within cities, but between cities, where do you think they are? Most people are going to tell me, well, aren't they with the electric lines? We see those big power lines, or maybe with the telephone cables. And at least in the US, they're not. Where they are is next to the rail lines, because rail lines are, direct. They have a full right of way to go between cities. So that's perfect space. That's perfect for those cables. And so then you have those now telecom cables just beside the railways to, cross cities. So that's where, a new infrastructure was sort of integrated with an existing infrastructure, just because they had some similar properties. So can we do that? If we can do that, if we really, really need to build something, Can we make it multifunctional? So instead of just building a new road for cars, can we also build a new road not only for cars, but we make sure that it has some stormwater management features, and maybe we also put some sensors to do something, or maybe it also benefits all infrastructure systems together. We make it multifunctional, and that's something that we're not doing right now. But I do think that it is one of those traits that's coming up more and more in the practice, which is multifunctional infrastructure. The nice thing also about multifunctional infrastructure is that all of a sudden you give more value to the infrastructure system. And because you give more value, you're going to be better at maintaining that infrastructure. So that's one. And then the last one, which is way more nebulous, but I think is there as well. It is, can we design for specific interdependencies and decentralize is possible? So we will have interdependencies no matter what. They're always there. Can we at least take them into account and try to design for some? So that's eventually what we want is for interdependencies, instead of being limiting factors, that they become enabling factors. That's my little 4-step design process. So we went over urban engineering, some machine learning, and that urban infrastructure design process. There's a lot of things I could have talked about that I didn't. I do have now a pretty big COVID-19 travel-related behavior and attitude change research going on. It's on covidfuture.org. We have a big survey. It's me, a few people at UIC, and with Arizona State University. I've interviewed about 9,000 people in the US, so we have tons of data. It's all going to be public, so we can talk about that at some point. I have a student looking at water, electricity, and gas. Also now is looking at transport and electricity interrelationship. So we have some smart meter data and some highway traffic data. So I'm trying to see, can we use highway traffic data to predict electricity, and can we use electricity to predict traffic? Just because if people are on the road, they're not at home consuming electricity, and then they're at home consuming electricity, they're not on the road. So there are some interrelationships that we're trying to capture. I also have a student looking at green infrastructure design. So we have green infrastructure, low impact development, if that's something you want to do. I also have a student looking at urban intelligence, really trying to make sense of all that smart cities business. There's so much into it. What's there? Trying to make some order into all that landscape of everything is going on in the smart cities business. I have a student funded about train delay prediction modeling. I know that's something you want to do, but it's he's self-funded, so that's what he does. And then there's a side project with some colleagues in Singapore about water circularity in cities. Again, there's a bunch of stuff we can talk about. I really try to limit it to something that would be hopefully relevant to you. But that's about it. So now we can go to the questions. And I did see a couple of questions in the chat.
Yes, great. Well, so first of all, thank you, Sybil. Yep. That was a really exciting talk, and I have some things to say about it, but let's move straight to questions, actually.
And I do have some time, by the way, after the hour. I can stay around, absolutely. Could you say a bit more about the criteria you use to decide whether your ML models provide good inference of the system? Well, that's a great question. That's a great question. There are a few metrics that we use. One that we like is SHAP that I showed you. That's Shapley Additive. I forget exactly what it stands for. That paper, by the way, is on Archive or Engineering Archive, and it will be published. It was just accepted. So SHAP was pretty good to tell us at least that hierarchy of variables. If you do any decision tree modeling, random forest, there's something called feature importance, and feature importance tells you the importance, like the name part of each variables. And I don't know how much you know about decision tree learning. It's actually a very, very cool algorithm. Then you have ensemble techniques, and they really make sense, and they tell you something about, again, your variables. And so that tells you something about the importance of their variables. And if you don't think that the tree or what you come out makes sense, then you just throw it out. There is something called partial dependence as well. That's really cool. That work a little bit like sensitivity analysis by increasing or decreasing the values or something. You see how it impacts on a dependent variable. So travel mode choice, for example, if all of a sudden I increase parking price, I can see how it would impact other things. Or let's say I increase parking price while at the same time decreasing transit fare. What would be my impact on cars? And if you look at the results and you don't think it makes sense, it doesn't make sense. But otherwise, it's just a new way to it's just different metrics to be able to look at your system. So I'm hoping I know at the end of the day, you're the human, and so you have to do the inference yourself. You have to see whether it makes sense or not. But there are metrics that you can derive from your models. Robin then saying, given the distrust of algorithms, how difficult is to convince decision makers of the need for change using machine learning models. Decision makers actually don't care. In my experience, they want to make sure that what they do in the end is important for their constituents. But whether you're using a very sophisticated machine learning model or very simple linear regression, they don't really care. Again, that's my experience. What was more difficult is to convince the community that machine learning, especially the transport community, and I'm really fed up with them, to convince them that machine learning was valuable. They were saying, well, that makes no sense. We have all those models that are great. And I say, well, yeah, but statistics, has been developed for 200 years. Give time to machine learning. It is promising. It is about 20, 30 years old now only. So it is promising. So look at the promises. And it's funny because 5 years ago, I would present and, I would just get negative feedback from anything machine learning. And now what I see is machine learning everywhere. People, I think, and it was the same thing with network science. I remember trying to publish a paper on network science and transit and really having the editor say, I don't believe in that stuff. So it rejected, not even go for review because the editor didn't believe in that stuff. And the same journal 10 years after and had an entire special issue on network science and transit. So it's incredible how trends evolve. So what I would say is, be open-minded, really be open-minded to machine learning models. Do try to do a good job, learn bit by bit, and what we've managed to do, at least in my group, is to publish along the way. So we learn and publish. But yeah, be open-minded. And if you're open-minded, other people will be. Sorry, go for it.
I think we've had some problems with algorithms and decision makers here. And they've had their fingers burnt because the models weren't very good. The first one was trying to allocate student grades by algorithm without doing exams. And that caused a lot of problems. We've had something similar where epidemiological models have been used in COVID. That's more statistical problem, I think.
Well, I'll tell you, I'm not worried about the research community too much. I am worried about the tech industry because they don't tell you about the models. They're not transparent about what they're doing. They're just trying to sell their product without really telling us what they're doing. That I'm really scared about.
That was part of the problem with the school grading exercise, that the system wasn't transparent, and when they forced to look at it, some quite simple errors, which were errors of domain knowledge, basically, were made by over-enthusiastic modelers.
There's one thing I know. The other thing that scares me is that a lot of the innovations right now in cities are driven by the tech industry. And I'm really worried because they know very little about urban planning and urban design and urban engineering. So I'm very, very scared about that. I remember talking to someone who was working with or knew people at Sidewalks Lab. That's Google's urban design arm. And they were telling me that it was full of computer scientists. There were no urban planners. And so what they were doing was not very relevant. And I know Sidewalk Labs, they were in Toronto for a few years, part of that revitalization project of the Portlands. And they just came out recently. I mean, I think they were essentially kicked out just because they were not doing a good job. And they were just trying to force their product. And then the teams, I think they had very, very few urban planners. So I am really, really scared about the tech industry because they're extremely good at marketing their models and they're not necessarily doing a good job.
And we've certainly had experience of that in this country.
There was, just looking back in the chat, I see there was one question about what are you, from James Bristow, on what are your views on digital twins?
Oh, that's a great question. That's an amazing question. I actually have a pre-proposal now about digital twins. I think it's a means to an end. Will we ever be able to really have digital twins of entire cities? I don't think so. Now, we do have very large models for transport, for hydrology, for building energy modeling that normally should inform decision makers and should inform us about what we should do. Will we ever be able to have a digital twin of a city together? I don't know. Several companies claim that they do have it. I don't know if they do, but I do like the buzz around it, just because I do think it can provide some funding to do some work toward not necessarily digital twins, but improving our understanding of cities through models. So am I a big fan of it? Not necessarily, but I do think that there are a means to an end.
Great. So what I'm just going to do now, since I'm aware of the fact that it's 6 o'clock, is I'm going to stop the recording, and I will create 2 breakout rooms, and perhaps Sybil and I will go into breakout room 1. And if you'd like to continue the more academic discussion in breakout room 1, or if you'd just like to catch up with, fellow colleagues or students, we'll go to breakout room 2. But before we do that, I'd just like to say a really big thank you to Sybil for a fascinating kind of tour de force of different ideas and the connections between them, and looking across disciplines, and also being really open to the limitations of each approach. I thought that was really refreshing, and really enjoyed it. So thank you very much.
Thank you. Just before we're done, I know it's 1, but there is one more question that I think is really relevant, which is basically about the fact that people should think more about not the infrastructure, but the people. And I absolutely agree, Jorge. I know. So usually the way we do it, I don't know how you do it. Usually we do it here is we have technical people together, and then we bring 1 urban planner, 2 urban planners, some social scientists. They're the token social scientists, and we want them to kind of inform us on things. But I really think that engineers have to change. I think engineers should really change and be way more people oriented. I can tell you that in my assignment for the winter break is I've got a couple of books on moral philosophy. And I want to learn more about moral philosophy. I want to learn more about social justice, about environmental justice, not so that I can do the same thing, but I bring them those elements from outside, but to make those elements central to what engineers do. And I do think that the role of the engineer will have to fundamentally change in this century.
Great.
So wish me luck. I'll have to learn about Kant and all those other philosophers.
Great. Well, thank you very much. I really appreciate it. And as I'm sure to the people on in the Zoom session. So I'm going to stop recording now. We'll create the breakout rooms, and I hope to see you.